Okay. This is in regards to the recent VenomFang video. He's trying to put a number on the complexity of the human body. Now, he's actually counting basically every single part of the body and trying to add that into his little straw man argument. The truth is, thanks to genetics, and no, genetics cannot be excluded in this. I'm sorry if he wants to do that, but you can't, because the genetics are what determine how the body develops. So with any organism, it's the genetics that determine how that organism develops. But if he's looking for a probability, then we have to look at actually what processes are involved in changing how those organisms, how aspects of those organisms are expressed. And that is the genetics. So you cannot exclude genetics from a question like this. To do so is to basically limit the question in such a way that, first of all, the question itself is meaningless, and secondly, you're hamstringing anyone that has a valid answer. And you're doing this, because you know it cannot be answered. Of course, that's not really what's going on in the world. His little ideas and his belief that he can actually control how things are and redefine how we, discover things and how we explain them. Well, it's not allowable if you want to have truth. If you don't want to have truth, you can do whatever you want. You can put together any kind of fictional argument. But we want truth. We want to know how things really are. Now, if we start with the earliest organism that we could call an organism that actually has a genome, whether that genome be RNA or DNA, but let's go with DNA right now. We can start beginning to calculate how many things are needed to produce what we see today. A good example, if you take a look at modern day genetics and measured rates of change in the genome, i.e. the mutations, we know that per base pair, and this is an average now, there's several different types of mutations. There's point mutations, there's duplications, the complete transporting of genome sections from one part of the genome to another. There's several different types of mutation events. But if you just average them out for point mutations per base pair, for most eukaryotes, it's about 10 to the negative fifth, give or take, mutations per base pair. If you actually break down the calculations with that, and I'm going to do this on my computer, we have 10 to the negative fifth mutations per base pair, and let's just give the standard human diploid, which is approximately 3 billion for the haploid. For the human diploid genome, which is the genes from both parents, we have roughly 6 billion base pairs. So we multiply that by 6 billion, and we would have a mutation rate of about 600,000 mutations per generation. Of course, this is for general eukaryotes. The truth is, human mutation rate is actually about 2.5 times 10 to the negative eighth. So let's work with that one. So we have 2.5 10 to the negative eighth, multiply that by 6 billion, and we have a number that's fairly familiar to me because I've crunched these numbers before. We have 150 averaging base pair mutations in the human genome per generation per person. If we just take a look at how many people on Earth today, which is about 6 billion. So we can multiply that by 6 billion. And we have 9 times 10 to the 11th mutations that exist in the human population today. There's approximately a 1% chance of a beneficial mutation occurring. 97%, 95% around there of totally neutral mutations. And the others may be a little bit deleterious, or, of course, others are totally deleterious. They kill the organism right from birth or from inception. So let's go with beneficial mutations. So we multiply that by 0.01, and we get, in the human population today, we would expect to find, if we could actually sequence everyone's genes and know exactly what's going on, we'd expect to see 9 times 10 to the 9th, or 9 billion beneficial mutations just in the human population at this moment. That's a lot of mutations. That is equivalent to 1 1/3 times more base pair mutations out there than there are base pairs in our genome. Mutation is very powerful. It can do a lot. And now these are the beneficial mutations. We're not even talking about just neutral mutations, which again I mentioned earlier, it's going to be 95% of that earlier number, which just to do the math, let's do it. So it's 9 to the 11th times 0.95. You get about 8.5 times 10 to the 11th neutral mutations in the population. So that's how we figure it out. If we actually calculate these and extrapolate back through time, the number of mutations that have been possible, and beneficial mutations only, and I crunched the numbers before, and this is very general math. I'm not like, breaking down for every animal's genome, because that's a lot more math than I care to do. We would have somewhere around the order of 6 to the 15th or 6 to the 16th base pair mutations throughout history. So we have that. We know this. We can measure it. This is what the math gives us. Is that enough to account for, well, what we see in humans today? Yes. Now, with that said, we need to talk about his little ideas of complexity. In my cupboard, I have salt, a crystal of salt. Each atom in that crystalline salt is in a very specific place. There are trillions upon trillions of atoms lined up in a perfect crystal lattice in that in those salt crystals. Sounds pretty complex. I mean, they're lined up in many cases overall more efficiently than what humans generally build. Sometimes we build some really strictly controlled things that are very specific and very accurate, but generally they're more accurate than anything we build. Now, when you break something down to its parts, you can always make it sound a lot more complex than it really is. There's no doubting that a human is complex, but so is an alligator, so is a shark, so are even smaller organisms like insects. They're all complex, but they're not complex because of the number of parts they have. And their complexity is not evidence against a natural process. The salt crystal forms via a completely natural process. Organisms and their change over time happens with completely natural processes.